This is a December 16 update on 3i Atlas based on telescope images and measurement graphs from recent scientific papers. In this video, we will go through what the images and graphs actually show, and if this helps you understand 3i Atlas, give it a like and subscribe. What you're seeing here are telescope images of 3i Atlas taken on multiple nights. Each panel shows the same object, but on different dates as it traveled closer to the Sun. The bright white area at the center is not the solid nucleus. Instead, it is the coma, a cloud of gas and dust surrounding the hidden core of the object. At the very center, there's a black oval that blocks the brightest region so that fainter features around it can be seen more clearly. White contour lines spread across the images, showing areas of equal brightness, similar to elevation lines on a topographic map. This helps highlight subtle structures in the dust cloud. Now let's focus on the arrows. The yellow line marks the direction of a narrow feature in the dust, which scientists interpret as a jet coming from a specific region on the object. The red arrow shows the object's motion or projected velocity, while the yellow arrow points away from the Sun. You can also see orange lines, which indicate the average orientation of the rotation axis, and additional yellow lines that trace the general tail direction. If you watch closely, you'll notice that the yellow line marking the jet changes direction slightly from one frame to the next. This change is not random. It follows a consistent pattern showing that 3i Atlas is rotating and that the jet is coming from a stable source on its surface. Brightness contour lines overlaid on the images use 10 logarithmically spaced levels ranging from the 20th to the 95th percentile of pixel brightness, making it easier to see the differences in the surrounding dust. Moving on to the graph, it shows the phase angle of the anti-tail jet over time measured at a distance of 6,000 kilometers from the brightness peak. The vertical axis shows the jet's direction in degrees, while the horizontal axis represents the rotation phase of the object. Each dot is a measurement from a different night. You can see that the points form a smooth, wave-like curve. This tells us that the anti-tail changes direction in a regular, repeating way, rather than randomly. From this pattern, scientists calculate that the jet completes a wobble every 7.74 hours, which implies that the object rotates fully roughly every 15 hours. The horizontal red line on the graph represents the mean position of the anti-tail. In simple terms, it shows the orientation of the rotation axis as seen from Earth, essentially how the object spins in space. All of these observations were made using the 2-meter twin telescope, or TTT. This telescope does not directly see the solid nucleus, but it measures patterns in the surrounding dust cloud. Observations were taken over several weeks, and the anti-tail jet is consistently visible. The periodic wobble confirms that the jet comes from a fixed spot on the rotating nucleus. In short, what we see in both the images and the graph is a sunward-pointing anti-tail that wobbles in a regular pattern. This wobble is caused by the rotation of 3i Atlas and a jet that is slightly offset on the poles. Studying these features helps scientists understand how this interstellar visitor behaves and what its physical characteristics are. Although the behavior may look unusual at first glance, scientists emphasize that jets that wobble due to rotation are well known in comet science. Anti-tails can form simply due to dust geometry and the viewing angle. All conclusions here are based on known physical processes. No part of the data requires non-natural explanations. As 3i Atlas moves farther from the Sun, its activity will fade. Future observations will test whether the rotation period remains stable and whether additional jets appear. Each new interstellar object will help scientists compare patterns and refine these models. For now, the images and graphs show a rotating object releasing material in a structured, predictable way, consistent with cometary physics. The value of this data lies not in speculation, but in how clearly it allows scientists to measure motion from millions of kilometers away. If this video helped you understand 3i Atlas better, give it a like and subscribe and turn on the notification bells.